Okay, good morning. We're back. Okay, I'm sure everybody missed me a lot. You know, full day off from calculus. It's tough. Well, I'm sure it wasn't a full day off for you for calculus because you studied a lot, probably worked on some PFA studying, etc. So, yes. Good morning. Man, I can't believe I didn't stream for one day and I lost 500 subscriptions. Dang it. That's what happens, man. You got to stay on the grind. So you should see. I did get all my scoring and grading done yesterday. So you should see either a score in Summit. Well, I think most everyone. Well, no, there's some. You should have either gotten a score in Summit or I emailed you, or maybe both even. All right, there were several people that I emailed some feedback to for like major things that if they needed to fix or wanted to improve scores on, then I sent you some things that you could work on to do that. All right, not to everyone, but some. And again, if I didn't email you and I gave you a score and you don't like that score and you want to do something about it, then just let me know. We can talk about what that looks like. Okay. Everyone having a good week? We're at Thursday. You guys doing well? I hope. In general, not just with math, with anything. Time isn't real. Well, hold on. I mean, it is. Yeah, RJ, you didn't send a meme. You told me you were going to, and you never did. I was crushed. That's why I gave you a 0 on the performance test. In general, less memes than I expected. I'm not going to lie, I was pretty hopeful that I was going to get a lot of quality memes, or at least like a meme from most people. Didn't happen. Some people did. Some people sent in some really good stuff, and maybe I'll pull those up tomorrow and show them. There was a few really good ones, but I did expect more. I won't lie. It's just because I have such high expectations of you. Yeah, I did. Uh, yeah, Hayden was far and away the winner here because he sent in, I don't even know how many. It feels like it was like 10 that were high quality. right? Other people had good ones they sent in too, but Hayden just sent it. The quantity and quality that Hayden sent in was top notch. You guys have let Hayden establish himself as the funniest person in the class, so I hope you're happy about that. This is your doing, not mine. All right, had some good calculus related memes, had some good RJ memes, had some good, Mrs. Lee memes. It was good. Well, this is so sad. Hayden is your fault. That's right. Don't blame me for Hayden. Only blame yourselves. Remember, Hayden wasn't even in our class, you guys. We started the year no Hayden. And Hayden just busts on the scene, apologizes for nothing, destroys the meme game, and just takes over. Alexa, play Despacito. That should be one of my chat commands, right? Where they, I'll have the text to speech read out the donations. So some good stuff. There's still time. I'll go through and compile this tomorrow, and we'll show them and talk about them tomorrow. So if you have more memes or a meme that you didn't send in before, send it to me. Let's get it going. Don't let Hayden win. But all right, well, let's go on to our next review. So I sent you this morning this notebook file, a PDF that has all 4 of the questions in it, and the scoring guide for the PDF. Okay. So just further kind of review of things. It's no longer up to them. This one goes back to a lot of the stuff kind of that we worked on towards the end of the semester. All right, so let's look at that. Number 1, let R be the region in the first and second quadrants bounded above by the graph of y equals 20 over 1 plus x squared and below by the horizontal line y equals 2. All right, so first on, let me get a graph going. You would have your graphing calculators for this. Let me pull up a graph here so we can kind of better see what's going on. Just pulling up Desmos. Okay, so here is this curve, right? We have this red curve is the 21 plus x squared. So this is the upper boundary. Then we have y equals 2, which the problem tells us is the lower boundary. So there's this area in between here, which I don't think you can see my mouse, but you can see where it's basically like this. It has that flat bottom, and then the curve goes on top of it. So we're talking about that area between these two curves. All right. So it kind of right, not a perfect representation, but kind of looks like this. And so what we're asking about is this red shaded region is R. Okay, so part A says find the area of R. All right, well, this is a pretty simple one. is if we're trying to find the area between two curves, it's just the upper curve, or outer curve minus the lower curve or inner curve. All right, so the integral of, all right, the upper curve is 20 over 1 plus x squared minus the lower curve, which is just y equals 2. Okay, but now the question is, where exactly are my bounds? Right, I guess I should have dx here. Right, where are my bounds? So let me go back up to here. If you're doing this on Desmos, which is an option, sorry, okay, got it here. Which is an option, right? Since you'll be doing this at home, this AP test, you could have Desmos on your phone. There's a Desmos app, or you could have it on, if you have a separate screen or computer, you can use that. And if you look on Desmos, if you want to know where two lines intersect, you can just hover over the lines and the point will come up, and you can just click those points. If you're doing this on your graphing calculator, you would have to graph the two and then go to second, trace, intersect, so that it can calculate where the two lines intersect. But either way, you would see that they intersect at -3 and +3, right? The x values, -3 and +3. So that's what I'm going to use as my bounds. So this is -3, +3. Okay, and that's it. That's just my integral. I would use my calculator to evaluate this. I would plug all this in, integrate it. 37.961. Do you guys remember how to type in integrals on your calculator? You want me to show you? You want me to bring it up on I can bring up the TI-84 on screen. Or do you know? Do you remember? Math 9, baby, that's right. What's a calculator? It's used to measure time. But yeah, okay, like they said, Math 9. Okay, part B. Find the volume of the solid generated when R is rotated about the x-axis. All right, so rotated around the x-axis, you might remember from the end of AB, we have to choose between two methods on should we be using the disk method or the washer method. Right, so the idea here is that this whole red region is being spun around the x-axis. And the way that we determine which method should we use is we talk about, is it flush up against the axis? Right, so in this case, we do want to use the washer method because there's this gap between the area and the x-axis. Right? If that area were right up sitting directly on the x-axis, then we would use the disk method. Right? But we have to use the washer because there's the gap between it. All right. So we go through our setup of the washer method, which is, let me use volume. Okay. from -3 to +3 again, since that's the region of the x-axis or the x values that we're going to be rotating. And we have this squared minus 2 squared. I guess I don't need to write this. Dx. Okay, so this is based on the area being pi r squared. And so the radius, so like if I wanted to know what is the length of this yellow line, well, it's whatever that y value is for the green line minus the y value for the blue line. Okay. So that's why we're kind of doing this subtraction piece. Basically, we're taking, in order to get the washer, we're taking the area of that full outer circle and then subtracting the area of the inner circle, right? So that we just have, that kind of donut where we don't have the hole, but we have that outer piece. All right, so there's the integral setup. Again, just type this into your calculator, Math 9. We should get about this. Okay, if it were just like this, then we would use the disk method because it's right up against the x-axis. So our integral would just be pi integral of -3 to +3, 20 over 1 plus x squared squared. And we wouldn't need to do the subtraction part. All right, we wouldn't need the -2. Okay, but that's only if it's right up against the x-axis. All right, but since there's the gap, we use washer. Mental math, right. Just do that integral in your head. It's really not that hard, you guys. Come on. All right, at this level, you should be able to do it. All right, let's go see. The region R is the base of a solid. For this solid, the cross sections perpendicular to the x-axis are semicircles. Oh, jeepers. Okay. This always trips me up. I have to think really hard about this. Luckily, I already thought really hard about it last night whenever I did this previously, which means there's probably only a 54% chance that I mess up. Okay, so R is the base of a solid. So what that means is that red section, R, is the base. So imagine that we are looking straight down at that shape. Right? So if we're like flying overhead, we have bird's eye view, we look down at this three-dimensional shape, and this is what we see. Okay? So that's not very accurate. It's kind of more like this. Right? This curvature here, and it the curves keep going. But this inner region is the R. And so what we are told here is that the cross sections are semicircles. Right? The cross section's perpendicular to the x-axis. So what that means is if I slice straight down through this, right, what I would get is a semicircle, right? Or if I slice straight down through this over here, a semicircle, or this slice, semicircle, or this slice, semicircle. Okay. So again, the thing to always remember, which I always kind of forget, and I have to think really hard to make sure I remember, the shape that we're looking at, we're looking down at the region from overhead. All right, so it's like I'm standing over it. If I put my hand down on top of it, I can feel this curved, smooth top. And then those solid red straight lines, those are the bottom. Right, the bottom is flat, but that top has this semicircular shape to it. Okay, so let's, hold on, let me see if I can pull up. A good visualization. I don't know if I can really do this on Desmos. Maybe not. Okay. Well, forget it. So let's just look. This is confusing to me. If the shape is the base, how semicircles? What do you mean? When I say or when we're talking about the shape is the base, so this, right, so this green portion, that is on the ground, that is touching the ground. That bottom is flat, it's touching the ground. Okay, the part that is coming like up, like out of the page, like out of the screen, those dashed red lines, you have to imagine are jumping out at you. Right, that curved part is sticking up out of the screen. Are we, I don't know, how let me see if I can, it's hard to get, I've tried to look for like good websites that will take your 2D shape and then the shape of the cross section and then transform it so you can really see the 3D instead of just having to imagine it. But I haven't really been able to find anything great. This is the weird part of calc. Yes, this is the weird part that doesn't make sense. Ha 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 ha. Just this one. Just this is the one part. I do understand all the other parts, so it's just this one that I don't. Yeah, that's we all agree. All right, so let's talk about the area of this semicircle. All right, let's just, before we do any integral or anything, let's just think about the semicircle. Okay, so in general, area of a circle I know is pi r squared. So semicircle, right, it's just half of a circle, so area would be 1/2 pi r squared. Great. Now let's think about those. If it would write, let me write in yellow. Okay, let me think about this yellow piece here. What is the length of this? Well, it starts up here at this point and ends down here at this point. So if I knew what those 2 points were, if I just subtracted the y values, that would give me that length. Right, so this is that upper y value, which we know the upper y value is from this curve, 20 over 1 plus x squared, minus the lower y value, which is just 2. Okay, so it's whatever the height of that upper curve is minus 2, since 2 is the lower. That gives me the full length of that semicircle, right, or that diameter of the semicircle, but I don't want the diameter, I want the radius. So if that's the diameter, okay, that's great, that does help, because then I know the radius must be half of that. All right, so it's just the same expression I wrote for the diameter except 1/2 of it. All right, so let's go back to actually just the area. So area equals 1/2. Now that's a different 1/2. That 1/2 comes from here times pi times r, which r is 1/2 20 1 plus x squared minus 2. And then that whole thing is squared. So this expression now is the area of one of those semicircles. Right, but I don't just want one semicircle. I want a semicircle for every slice of that 3D shape, right? Because we're trying to take the volume. So area is a two-dimensional measure. So let's transform it into a volume by saying, okay, add up all of these semicircle areas along this, line from -3 to 3. Well, how many semicircles do we want? We want an infinite amount because we want to make infinite slices so that we can add up all of them perfectly. So what does that do? That just means we need an integral. So we're just integrating this area. Right? That takes it to 3 dimensions, which gives us volume. I'm going to go ahead and leave the 1/2 and the pi out here. This. If we wanted to, we could. Oh, let me write. Okay. We could sort of simplify this a little bit. So each of those yellow pieces that I circled would get squared. So 1/2 squared is 1/4. Pull the 1/4 out into the front. 1/4 times 1/2 is 1/8. Times pi is pi over 8. -3 to 3. 20 over 1 plus x squared minus 2 squared dx. So it's just a little bit nicer to work with and probably easier for me to type in rather than worrying about parentheses inside of parentheses and things like that. So if we type that integral into our calculator, right, math 9, should get about 174.268. So that is the volume. All right, so for the cross-sections one, all we have to do is just find an expression that represents the area of one of those slices. Once we have an expression for the area, then just integrate that across, whatever the x value should be. So in our case, -3 to +3. But it is confusing. It's tough to visualize. Right, but those dashed semicircles are coming out of the screen. Okay, let's take a look at number 2. Let f and g be the functions given by f of x, 1/4 plus sine of pi x, and g of x equals 4 to the negative x. Let R be the shaded region in the first quadrant enclosed by the y-axis. Let S be the shaded region in the first quadrant enclosed by the graphs of f and g as shown in the figure above. Find the area of R, find the area of S, find the volume generated. Okay, great. So first, we just want to find the area of R. All right, so trying to find this red region. This is very similar to what we just did on the last one, right? For our part A, right? The area between two curves. We just take the integral of the outer curve minus the inner curve, the top curve minus the bottom curve. Okay. So, which is my top curve here? Well, it tells me that's g of x, right? So I can see g of x is the one, at least for R, that is the one that is the top of it. So the integral of 4 to the negative x minus the lower curve, which I can see is made by f. F, the problem tells me, is 1/4 plus sine of pi x. And dx. Now the question is just, what are my bounds on this integral? Well, I know the first bound should be 0. Right? I can see that's where the region starts at x equals 0. But now the thing that I don't know yet, how far over should this bound go till it ends? Right? I don't know this x value, but we can figure it out. Just like I talked about on the last one, you can use Desmos. You can put it into your TI-84 calculator, graph those two, and then do second trace intersect. All right, and it'll help you figure out how to intersect. I'll just pull up Desmos again. Get rid of these. So let's graph our new ones. 4 to the negative x, 1/4 plus sine of pi x. Remember on Desmos, if you just type whatever you want, it'll do it. Right, like pi, pi, or if you want to do an integral, type int, or if you want square root, just type sqrt, or whatever. Right, you can type anything in that you want. Desmos will know what you mean. It's pretty smart. Okay, so now this doesn't look like my graph that we were given, but if I zoom in, I can see, oh, okay, yeah. So R is this region right here. All right, this is more what my picture looks like with the R and the S. So my question is, where do these two points, or where do these two curves intersect? More specifically, what is the X value? So I can see 0.1782. You would get the same thing if you used your graphing calculator. All right, so I use 0.1782 as my upper bound. Now I have my full integral that I need. Let's just type that in. Math 9. .064. Gosh. Okay, part B, find the area of S. All right, so now I want the blue region S. So same thing. Integral of the upper curve minus the lower curve. So the sides swap. Right, so now F is the upper curve. So that means my 1/4 plus sine pi x is the upper curve minus the lower curve, which is g of x, so minus 4 to the negative x dx. Now, what are my bounds? Well, I know they start 0.1782. And now the thing that I don't know is, where is that upper bound? We can do the same exact thing. Use your calculator, use Desmos, use whatever. Okay, just do it in your head, I guess. Oh no. I lost it. Nope, I'm good. Okay, so let's scroll over a bit. So now we're looking for this point where they intersect. And I can see they intersect at 1, which is nice. Okay, so that upper bound on my integral is 1. Calculate it, math 9, or do it on Desmos. 0.410. All right, part C. Find the volume of the solid. Okay, so volume when S is revolved around the horizontal line y equals -1. Okay, so we did a revolution problem in our last problem on number 1. So this is just another revolution problem, right? And we're specifically looking at S. Okay. R is not being revolved. This specifically says S is revolved around the line y equals -1. So y equals -1 is somewhere down here. And we want to revolve around that. Ugh. Okay. So like with our last revolution problem, okay, like on part B from number 1, okay, remember it's basically just the area but integrated, right? So we're thinking pi r squared. And if we're doing a volume revolution problem, again, I have to decide disk or washer. Okay, well, very clearly, this should be washer, right? Because that region S, I think it's called, that region S is not flush up against, not the axis, because we're caring about revolving around here. So it's not right up against that, right? There's clearly lots of space in between them. So since there is that space, that tells us we're going to use the washer method again. Welcome to the Lisp game. Thanks. Been working so hard my whole life to get here. Dreams do come true. All right, so our integral. Okay, what should our bounds be? Well, our bounds are, remember, for region S, the bounds go from 0.1782 to 1. Stutter can't rip my speech therapist. Man. I need to get on a Zoom conference with my speech therapist. They watch all my live streams and critique me. They just keep sending me clip after clip of me saying stupid things. It's harsh. Very harsh. That reminds me. Uh-oh. Uh-oh. What are we reminded of? Zoom conferences. Uh-oh. Hayden's got to go. He's supposed to be somewhere. He's got a Zoom birthday party to attend. Okay, this is my integral. Now compare to our integral from before. Right, so we have pi, the bounds, -3 to +3. Right, the outer curve squared minus the inner curve squared. All right, so that's almost the same thing we have here. Oops, we need a pi here. That should still be the same. So we almost have the outer curve squared minus the inner square. No, that's not right. Inner curve squared. Holy hell. All right, so f of x squared minus g of x squared, but we have this +1 in each spot. Right, now why is that? Well, because since we're revolving around y equals -1, then if I think about what is the length of this yellow line? Well, if I knew the y value of this point, that would tell me how far it takes to get to the x-axis, but that's not the whole length that we want to think about since we're revolving around y equals -1, so we have to add 1 because we're going 1 more below the x-axis. Or same thing for the lower line. Well, the y value, right, just g of x would tell me the length from the curve to the x-axis, but we have to go further than that. We have to go down 1 so that we can get to y equals -1. So that's why in each of those, for each of those functions, we add 1 before we square it. Right? Because we have to account for going 1 more length of distance to get to y equals -1. Right, so it's a slight difference. All right, but then otherwise this is just a good integral we can get. Right, we know the I didn't write out the full equations, but we know what f of x is. We know what g of x is. Right, f of x is the 1/4 plus sine pi of x. G of x is 4 to the -x. So we just plug all that in, math 9, and we calculate. We would get 4.558. Okay, so that's a great review on volume of cross sections, volume of revolution, area between curves. Good stuff. Three and 4 we'll go through tomorrow. Would recommend going through tonight and looking at some of this. Like you could see 4, like even part A, area of R. Right, talking about cross sections, talking about revolution, right, volume generated rotating around the horizontal line, generated around the y-axis. Okay, take a look at these. Try to at least get an integral you can set up, right? Just to think about it. Then we can come back. You don't have to spend an hour on it, right? But at least try to set yourself up for practicing getting the idea of what these setups are going to look like. As always, I recommend going through studying the resources that you have from the AP test review or the AP review or AP test, whatever, AFA. Okay, especially, what is it? Let me pull it up. I can't remember what it's actually called. I forget what the actual resource is called. Give me a second. This unit makes my brain hurt. Yeah. I feel you. Okay, so this is a great resource. Okay, this is on Summit. It's like in that Objective 3 for the AP review. It's called BC Cram Sheet is what it's titled on Summit. But it's like has this title of BC Stuff You Must Know Cold. So this knowing cold means these are things that you have to be able to know that you can just pull off the top of your head, right? Things that you shouldn't have to like go look up the formula. All right. Again, and it's different because I know that you have the ability to do that, but you cannot rely on having to take the time to go look, search through your notes or do whatever to find these things. Must know freezing, right? You have to memorize these after you've stuffed yourself in your freezer. Okay, that's the only way. Scientists say that's the best way to make sure it stays in your brain. You don't forget it. Okay, but L'Hopital's rule, log properties, the differentiation rules, chain rule, product rule, quotient rule, have to just know them. Average rate of change, these various derivatives. Okay, curve sketching, that's about like the relationship between a function, its first derivative and its second derivative, inflection points, concavity, right? Euler's method, logistic curves, just various integrals. Okay, recognizing these trig ones down here, right? The U and the A's. Velocity, speed, distance traveled, disk method, washer method, known cross sections, Taylor series. Aha, we talked about Taylor series. So you know that perfectly. Ratio test, polar curve. Well, again, polar curves we don't actually need to know. They got rid of that. Polar curves, don't need to know it. Never mind. Arc length. For rectangular, yes. We don't need to know the polar one for this AP test, but arc length, yes. Integration by parts. Error bound, yeah, we did that. Alternating series. Right, most common series, geometric, P series, etc. Okay, so this is a great jumping off point of how well do you know these things? And I know it's a ton of stuff. I know it's a lot of formulas. Okay, I get that, but I mean, it definitely can be done. All right, students have been doing this for 50 years or however long this APBC test has been out. Okay, it's doable, certainly manageable, but it just takes some time. Okay, you have to be quizzing yourself, making flashcards. Just pull up this sheet and, or if you print it out and then just like cover up the rules and go through and try to see if you can recite them and get the rules correct, or the integrals or the derivatives or the, whatever. Average value. People always forget the 1 over b minus a on average value in front. Okay. Reese, Hayden. Logistic curves. Okay, we talked about this stuff. So this is, there's other formula sheets and review sheets on there as well. But this is a really good sheet that has everything condensed sort of together. right? So use that to quiz yourself, use that to study, make flashcards off of it, do whatever you need to do. Okay. I also had this was also another. So this is on the objective 2. It's called flashcards sorted by topics. So I showed you this in class one day, but it's AP Calculus BC flashcards, and it has just every single topic, right? Derivatives, velocity, Euler's method, L'Hopital's rule, finding maximums, mean value theorem, concavity, graphs, limits, continuity, polar, we don't need polar, integrals, initial conditions, distance traveled, accumulated change, volume of cross sections, and area, improper integral, substitution, et cetera, et cetera. Okay, this has at least a few. Some of these have a lot more, and some of these just have a couple. But practice for every single topic that is covered in BC. Okay, you guys know what you struggle with. You know what your spots are where you need to work more. So go into that. Take some time to do that. I can promise you're not going to do well in the AP test unless you take the time, a lot of time, to go through this stuff and make sure that you have it. Okay. Now I don't mean a lot of time, like 10 hours a day, but you have like almost a month, a little under a month until the AP test. Okay, that's a lot of time if you think about 30 minutes a day, even an hour a day. Now, an hour a day is a lot of time, especially when you have a lot of stuff. But, use your time, use your opportunity to not only know this stuff, but also, since you guys have the opportunity to have notes with you, okay, to organize things, to write things out, to have examples, things that you can do to make sure that when the AP test comes, if you do need to go look up something, which hopefully you don't, but if you do, that it's organized in a good way that you know where to find it, you have a useful example ready, or whatever it is. Absolutely everything several times. That's right. Okay, chunk it up. Say, you don't have to, I don't know. People do different things. Some people would just go through and study this entire paper in a day and then study the entire thing again the next day. Or some people might say, okay, today I'm just going to practice getting down these first 6 boxes. Make sure that I know those really well. And then, okay, tomorrow I'm going to go through and work on these 3 or 4 boxes where I'm going to make sure I have it memorized, and then I'm going to go do some practice from the flashcards, or I'm going to look through my notes and do some example problems over again. Or I'm going to practice this, and I'm going to go in and do the diagnostic on that PFA that's related to that. Or I'm going to take the PFA. Even if you've passed a PFA and you just want to practice more, go request a PFA again, right? I'll still accept them. I don't care. Or, okay, today I'm just going to focus on this volume section where it's the disk method, washer method, cross sections. And I'm going to study those formulas, make sure I have them down, do some practice problems from the flashcards or from my notes, etc. Okay. But it has to be that you're reviewing all of these things several times. Okay, in between now and whenever the AP test starts. Right, studying things once or twice, it doesn't get it stuck in there. Studying things multiple times over the course of several weeks, that's what gets things stuck in your brain. Am I lagging really bad? I think so. Okay. Okay, yeah, I don't know. My stream kind of weirded out on me. I don't know if you heard that last part, but again, the point is studying things multiple times over a long period of time. That's how you remember things. That's how you get good at things. All right, repetition. Not just the quantity of time. So it's not just I practiced this formula 15 times today. It's, oh, I practiced this formula 15 times today, and I did it 15 times on Friday, and then I studied it 15 more times on Sunday, and then the next week I studied it 15 times for 2 more days. Right? It's not just the quantity in an isolated spot. It's the quantity repeated over several days, several weeks. That's how you memorize something.